Welcome to the fifth and penultimate tutorial in this series on quadratic functions. In the previous tutorials in this series, we've looked at a range of different methods with their own terminologies to deal with quadratic functions, and I think because this topic has sort of a range of methods associated with it, it can be very confusing for students, because these methods are often taught at different times and they're not often sure how they're all related. So the purpose of this tutorial is to take one quadratic function and to find out everything about it using all the different methods. And so you'll see them compared side by side, and it will hopefully enable you to see all the very nice connections between the methods. In the final tutorial on this topic, which really is just optional because it's not covered at this level of maths, but I just wanted to use the method of completing the square on the general form of the quadratic function to derive the quadratic formula for you, so you can see where that very bizarre formula actually comes from. But anyway, for now, we're going to look at one example and just really sort of give it the works with every method. So I've just chosen this function, y equals x squared plus 6x plus 5. Okay, so let's look at this first from the point of view of roots. So let's approach this quadratic function from the point of view of roots. Maybe the very first thing to do, though, is just to notice that the coefficient of x squared here is 1, which is positive, so we know that we're dealing with a u-shaped or valley-shaped function. It's always good just to have that in the back of your mind. And we're interested in roots. So, does it have any roots? Well, let's look at the values of a, b, and c. A is 1, b is 6, c is 5. Let's work out the discriminant, shall we, and see. So b squared minus 4ac, so b squared will be 36. And then take away 4 times 1 times 5, take away 20 is 16, which is positive, and so we know that there will be two distinct roots for this quadratic function. Let's use the quadratic formula to find those roots. So remember the quadratic formula. I think you're often given this in exams. You're not sort of forced to memorize things like this anymore, at least not in Scotland, whereas when I was at school you had to. Of course, that was several hundred years ago, so times have changed. Right, so here's a quadratic, I'll never forget it. I can write it without even thinking, it's kind of scary. Anyway, it's minus b, so it's minus 6, plus or minus the square root of the discriminant, which we've already worked out, which is 16, divided by twice a is 1, so it's just divided by 2, and we get minus 3 plus or minus 4 divided by 2. So just again to say, if you're asked to find roots of a quadratic function, just to remind you, by saying roots we are basically asking what values of x does y equal 0. Now if you're asked to find roots and you can't see a way to factorize a quadratic equation, you can always use the quadratic formula. Here we have negative 3. Let's do the take away 4 first. So negative 3 take away 4. Oh, I beg your pardon. I've already divided by 2 just subconsciously there. Negative 6 take away 4 is negative 10. Divided by 2 is negative 5. And then negative 6 plus 4 is negative 2. Divided by 2 is negative 1. So there are the two roots, negative 5 and negative 1. Now, let's just see, could we have gotten that by factorization? So to find the roots, we're asked to solve the equation x squared plus 6x plus 5 is 0. Does that factorize? Well, 5 only really has one way of factoring it with integers, which is 5 and 1. And indeed, we see that we do get 6x, x squared, plus x plus 5x is 6x plus 5. So that's all fine. This will be satisfied if either bracket is 0. If this bracket is 0, that occurs at x equals negative 5. If this bracket is 0, that occurs at x equals negative 1. And so from factorization, we could also have found the roots. So that's all fine. We have the roots. We know it's a U-shaped function, so we can sort of plow ahead here. X and y. That's at the very outer edge there, put negative 5. So it's kind of like 1, 2, 3, 4. So maybe 1 is sort of there. There's the origin. So these are the two roots, negative 1 and negative 5. And using our general knowledge of quadratic functions, we know that the mirror, the axis of symmetry, lies midway between the roots. So that will lie at negative 3, okay? So there's the axis of symmetry. So the axis of symmetry is x equals negative 3. Perhaps I should have stressed this more in earlier tutorials, that when you're asked to describe the mirror or the axis of symmetry, it's not enough just to give a numerical value. They want you to say x equals negative 3, because this equation describes the entire line. So just to note that. We can plug x equal to negative 3 into our quadratic function to see what the value of y will be at that value. We know it's going to be negative because otherwise we're not going to get any roots here. So let's just do that. So y when x is negative 3 equals x squared, so negative 3 squared is 9, plus 6 times x, 6 times negative 3 is negative 18, and then plus 5, which is minus 9 plus 5, which is minus 4. Okay, so that's going to be the turning point then, is that y is negative 4, x is negative 3, there's the minimum, and we'll have then this quadratic function. I've not drawn this very well. Sorry, I'm going to just shift this up, otherwise I just didn't choose the y scale very intelligently, otherwise I can't really get the curvature in my sketch. There we go. There's the function. And symmetric about the axis of symmetry, x equals negative 3, roots negative 5, negative 1. Yeah, I think that's all one can say about the quadratic function from the point of view of roots. So let's just do this whole kind of finding out about the function from completing the square, including this sort of additional little bonus about finding the roots having completed the square, because I promised you that that's possible. Let's just see how you'd go about that. So this is now completing the square rather than looking at roots. This is actually similar to one of the examples we did in the last tutorial, because I think we had x squared plus 6x there as well. It's just that we have a different constant. So we ignore this, we look at these two terms, we write x plus half of this value goes in. Okay, so it's going to be x plus 3 all squared. But then we have to remember to subtract off the overshoot. The overshoot is 3 squared. So we get x squared plus 6x plus 9. We don't want the plus 9, so we subtract the 9. This equals the first two terms, and then we bring back the neglected constant. And we have x plus 3 squared, take away 4. Wow, this is why I call this the prince of methods. Do you see how we've just cut to the chase, none of this messing around. This vanishing tells us the axis of symmetry. Okay, x equals -3. And we have, when this vanishes, we have y equals -4, which is the value of y at the turning point. So that was very nice. You might say, yes, but you don't know the roots. Okay, let's find the roots. The roots, after having completed the square, well, the roots are those values of x for which y equals 0. So we're going to take this form and set it equal to 0 and see what happens. So we have x plus 3 all squared, take away 4 is 0. We have to solve this equation for x. It's a good little practice in rearranging equations, actually. So we want to get x, so we want to take this over first of all. So I'm going to take that -4 over to the other side, where it becomes a +4. To get anywhere closer to x, I have to get rid of this square. So I'm going to take the square root now. And the square root of 4, it's very important to realize, has two values. It's either 2 or it is -2, because the square root of 4 literally means that number which when squared gives 4. And there are two values of this. One is 2 and one is -2, because either of these when squared gives you 4. So we have that x plus 3 is ±2. And then finally, just take the 3 over, we have x is -3 ±2, which of course gives us -5 and -1 as promised. So you can get the roots very easily having completed the square. It's really not very difficult. You might notice, look, over here when we used the quadratic formula, we got down to here. If I had divided by 2 at this point, I would have had x is -3 ±2. So that kind of gives you a hint that this quadratic formula somehow comes from completing the square. It does. If you complete the square on the general form of the quadratic function, you derive the quadratic formula, and that's what I'm going to show you in that last optional tutorial. But for now, I think it's time to close. I hope this last example's been useful to just get all the same information out, but using here, coming into the problem, focusing on the roots and ending up with the axis of symmetry and a turning point. Here, by completing the square, coming into the problem by identifying the axis of symmetry and the turning point, and then using this very elegant form of the quadratic function to quickly find the value of the roots. And just a reminder, if there are no roots, this method will not get you anywhere, whereas this method still works, and you will be able to determine the axis of symmetry and the turning point, no problem. Right, I hope that was helpful, and I'll see you, possibly some of you, for that optional last tutorial. So see you then.